Assalamualaikum and greetings. My name is Muhammad Hilmi bin Zakaria and my number metric B0819101116. This is a list of my group members. I will present about introduction of graph. So, what is graph? Graphs are a way to formally represent a network or collection of interconnected objects. In mathematics, graphs are defined as an ordered pair with two parts, vertices and edges. So, in order pair VE, which is vertices and edges, node or point, where V is set of node, also called vertices, and E is a set of edges, also called links. Graph underlie many computer programs that make a modern communication and technological processes possible. They contribute to the development of the thinking, both logical and abstract. Graph can have two types of edges, an edge that has a direction of flow and an edge that has no direction of flow. Edge can connect nodes in any possible way. There are no rules. These are not vertices and these are edges. So, let's look the different type of edges in graph. Directed edge. Two nodes are connected in a very specific way. In the example below, node A connect to node B. There is only one way to travel between these two nodes. Only one direction that we can go. In a directed edge, we can only travel from the origin to the destination and never the other way around. For undirected edge, the path that we can travel goes both ways. This is to say, the path between the two nodes is a bidirectional, meaning the origin and destination nodes are not fixed. So this is another example for direct and indirect.
Assalamualaikum and greeting. My name is Muhammad Shafiq bin Yaakob. My metric number B0819101006. Now I will present about graph coloring. What is graph coloring? A graph coloring is an assignment of labels called colors to the vertices of a graph such that no two adjacent vertices share the same color. Graph coloring is also called as a vertex coloring, or it can be also called as a properly colored graph. Here, I show the example of graph coloring. It has 5 vertices with a different color. It assures that there exists no edge in the graph whose end vertices are colored with the same color. Means all the vertices not share the same color. The rule to create the graph coloring, it need to no two adjacent vertices share the same color. Next is chromatic number. Chromatic number is the minimum number of color required to properly color any graph coloring, such that no two adjacent vertices of it are assigned the same color. Here the example of chromatic number. To count it, in this graph, it has 3 different colors, so mean the chromatic number will equal to 3. The rule is no two adjacent vertices share the same color. Means if the first vertex here connect with the other vertices, it need to be a different color. So the next one is type of chromatic number of graph. There are a few types of graph in chromatic number. Here, first, cycle graph. A cycle graph or circular graph is a graph that consists of a single cycle, or in other words, some number of vertices, at least 3. If the graph is simple, connected in a closed chain. As example, if number of vertices in cycle graph is even, then its chromatic number will equal to 2. As is shown in the example of chromatic number or cycle graph here, if the cycle graph is even, 4 vertices and 6 vertices, so the chromatic number will equal to 2 because the cycle graph is even. While if the number of vertices in cycle graph is odd, then its chromatic number will equal to 3. So if the vertices are 3 and 5, show the odd number, so the chromatic number will equal to 3. So the next one is planar graph. is a graph that can be drawn in a plane such that none of its edges cross each other. So means it's same with the cycle graph. So the chromatic number of planar graph is less than equal to 4. So the example of the planar graph. The third one is complete graph. It's a graph in which every two distinct vertices are joined by exactly one edge. They are also connected with every other vertex. Each needs as many different colors as there are number of vertices in the graph. So the example of chromatic number of complete graph. So this whenever the vertices are equal to 4, the chromatic number will equal to 4 also. So same here, even the vertices are odd or even, the chromatic number will equal to the same. Means chromatic number of any complete graph equal to number of any complete graph. So mean when the vertices are 5, the chromatic number will equal to 5. The next one is bipartite graph. It consists of two sets of vertices, x and y. X here show that x is equal to red vertex and y will equal to blue vertex. So the edges only join vertices in x, two vertices in y, not vertices in a set. Means for the x sets, it will not connect with the x set. So mean it will connect to the other set. Means x will connect to y only. Y also can only be connected in the set of x only. So for the chromatic number of any bipartite is equal to 2, 1 and 2. So for the last type, tree graph. It's a special type of connected graph in which there are no circuits. Every tree is a bipartite graph. So shown in the example figure, this is the first bipartite graph, this is the second one. So means every tree is a bipartite graph. So for the chromatic of a tree, which any number of vertices is also equal to 2. We use only two color to create the tree graph. Okay, that's all. Thank you.
My name is Muhammad Hakim bin Muhammad Hassan Al-Fahmi. My metric number is B0819100111. So now we go to the shortest path algorithm. In graph theory, the shortest path problem is the problem of finding a path between two vertices or nodes in a graph such that the sum of the widths of its constituent edges is minimized. There are several types of shortest path algorithm, but in this explanation we just go to the Dijkstra's algorithm. With Dijkstra's algorithm, you can find the shortest path between nodes in a graph. Particularly, you can find the shortest path from a node called the source node to all other nodes in the graph, producing a shortest path. The basic of Dijkstra's algorithm basically starts at the node that you choose, the source node, and it analyzes the graph to find the shortest path between that node and all the other nodes in the graph. The algorithm keeps track of the currently known shortest distance from each node to the source node, and it updates this value if it finds a shorter path. Then, once the algorithm has found the shortest path between the source node and another node, then that node is marked as visited and added to the path. The process continues until all the nodes in the graph have been added to the path. This way, we have a path that connects the source node to all other nodes following the shortest path possible to reach each node. So let's look at the example of Dijkstra's algorithm. During the execution of the algorithm, each node will be marked with its minimum distance to node C as we have selected node C. In this case, the minimum distance is 0 for node C. Also for the rest of the nodes, as we don't know this distance, they will be marked as infinity. Except node C, because we currently mark as a red dot. Now the neighbors of node C will be checked, which is node A, B and D. We start with B. Here we'll add the minimum distance of current node 0 with the weight of the edge 7 that link node C to the node B and get 0 plus 7 equal to 7. Now this value will be compared with the minimum distance of B, which is infinity. The least value is the one that remains the minimum distance of B. Like in this case, 7 is less than infinity and marks the least value to node B. Now the same process is checked with neighbor A. We add 0 with 1, weight of edge that connects node C to A and get 1. Again, 1 is compared with the minimum distance of A infinity and marks the lowest value. The same is repeated with node D and mark 2 as lowest value at D. Since all the neighbors of node C have checked, so node C is marked as visited with a green check mark. Now we will select the new current node such that the node must be unvisited with the lowest minimum distance, or the node with the least number and no check mark. Here, node A is the unvisited with minimum distance 1, marked as current node with red dot. We repeat the algorithm, checking the neighbor of the current node while ignoring the visited node, so only node B will be checked. For node B, we add 1 with 3 weight of the edge connecting node A to B and obtain 4. This value 4 will be compared with the minimum distance of B 7 and mark the lowest value at B as 4. After this, node A marked as visited with a green check mark. The current node is selected as node D. It is unvisited and has a smallest recent distance. We repeat the algorithm and check for node B and E. For node B, we add 2 to 5, get 7 and compare it with the minimum distance value of B. Since 7 is greater than 4, so leave the smallest distance value at node B as 4. For node E, we obtain 2 plus 7 equal to 9 and compare it with the minimum distance of E, which is infinity, and mark the smallest value as node E as 9. The node D is marked as visited with a green check mark. The current node is set as node B. Here we need to check only node E, as it is unvisited and the node D is visited. We obtain 4 plus 1 equal to 5. Compare it with the minimum distance of the node. As 9 greater than 5, leave the smallest value at node E as 5. We mark D as visited node with a green check mark and node E is set as the current node. Since it doesn't have any unvisited neighbors, so there is not any requirement to check anything. Node E is marked as a visited node with a green mark. So we are done as no unvisited node is left. The minimum distance of each node is now visited, representing the minimum distance of that node from node C.
Assalamualaikum and greetings. My name is Muhammad Adi bin Abrahman. My metric number is B0819102257. So the implication to real life based on graph theory is GPS. Using GPS or maps to determine a route based on user settings, quickest route or shortest route, or finding the cheapest airfare between two destinations. The destinations are vertices and their connections are edges containing information such as distance or airfare. The software finds the critical path, optimal route based on the user settings. Next is social media. Connecting with friends via social media or a video going viral. Each user is a vertex, and when users connect, they create an edge. Videos are known to be viral when they have reached a certain number of connection or views. After that, we have school administrating bus routes. School administration developing bus routes to pick up students. Moreover, we also use graph theory in city planning. Analysis of the spectral gap and the relative asymmetry distribution show a similar structure for these cities. The irregular or reticular housing structure seems to ensure connectivity and accessibility more than the regular grids. However, connectivity is ensured by the most peripheral streets, which in the space syntax representation play a marginal role. Lastly, we also use graph theory to solve Sudoku. Sudoku is a logic-based combinatorial number placement puzzle. In classic Sudoku, the objective is to fill a 9 x 9 grid with digits so that each column, each row, and each of the 3 x 3 grid subgrids that compose the grid contains all the digits from 1 to 9. The vertex that is already colored is selected and linked by edge of the same color with all the vertices of sets in which the vertex is located. These vertices can no longer be colored with the same color. This is repeated for all the vertices for which hints are given. The vertices where the largest number of colored edges converge are found. If there are vertices among them that can be colored only by one color, Then they are colored with it and the procedure continues from the first step. There is no need to draw those edges into the graph that lead to a vertex where there is already another edge of the same color. If there are no such vertices, the procedure continues with the fourth step. From the set of those selected vertices, the one that is adjacent to the largest number of uncolored vertices is chosen and colored to the color with the lowest value that is not used for its neighbors. If there are more such vertices, one of them is selected randomly. In the next step, the procedure continues from the first step.
We have come to the end of our video. So, my name is Muhammad Hazim bin Mazlan. My matrix number is B0819-10429, and I will recap about the conclusion for this topic. In theory, graph could be mounted as a set of objects structured in which some pairs of the objects are in a sense related to each other. We know that these so-called objects correspond to mathematical abstraction called vertices, also known as nodes or points. Moreover, based on this assignment, we depicted the various types of graph and the application of graph. We have also graphed the fundamental of graph coloring, which is a special case of graph labeling. Furthermore, by exploring in depth of the Dijkstra algorithm, we could conclude that it is one of the best algorithms to find the shortest path between nodes in a graph, given that it is basically picks the unvisited vertex with the lowest distance before calculating the unvisited distance through all the unvisited nodes. To conclude, graph theory is ultimately the study of relationships. Given a proper set of nodes and connections, which can be about anything ranging from city layout to computer data, graph theory provides a helpful tool to quantify and simplify the many moving parts of the dynamic systems. That's all from our group. Thank you for your time and thank you for watching.